lecture, I'm going to discuss about the laced compression member design. So the problem is design a built-up column of 10 meters span to carry factored axial load of 1080 kilonewtons. The column is restrained in position but not in the direction at both the ends. So based on this statement, we can calculate the effective span of the column. Effective span or effective length, which is denoted with LE. Okay. Then provide single lacing system with bolted connection. Assume steel of grade Fe410 and bolts of grade 4.6. And the problem is design the column with two channels placed back to back and design the column with two channels placed toe to toe. So in this picture I have drawn this figure is not given in the problem, so we need to imagine the channels placed back to back. So these two channels are facing back to back. If you want to draw this for channels facing toe to toe, you can draw like this. So this is facing toe to toe. So first of all, we are looking at the problem. The problem A, channels placed back to back here. So before going to the problem, so we'll see what are the things we have to calculate. Okay, so the given data is we know the factored axial load on the column. How much it is? 1080 kilonewtons. And what are the other things they have given? Steel of grade Fe410 and bolts of grade 4.6. So from this we can write Fu of steel is 410 Newton per mm square and Fu of bolt. Ultimate stress of bolt is 400 Newton per mm square. Then the span is given, span of 10 meters is given, and also the end conditions are mentioned. Column is restrained at position free in rotation. In the direction they have mentioned, but that is equals to rotation. So the column support can be rotated. So now we'll see in the table 11. You can see the effective length conditions. So here at both the ends, translation means position. It is fixed, right? So restrained and free we need to check where we can see. So it is restrained and free, restrained and free. So this is the condition you can say. Okay, this condition means both the ends we are having hinges, but they are restrained in the direction. So then the effective length will be 1L. Now the effective length LE equals to 1 into L. So that is 10 meters. So you can use this effective length. So before going to the problem, so I'll explain this figure also. So here the columns are placed back to back, but with some space that space we can call it as S. So, and these two columns are connected using the lacing system. So the lacings were shown here in this below figure, which we will be having side view. So the lacings you can see here. So these lacings will design later. First we need to design for the channels. So which type of channel we need to assume. Only as mentioned in the problem, only we need to take the channel sections here. Okay. So these are connected with the bolts. These lacings are connected to the channels using bolts. Now, the step one is we need to assume some stresses because as we know the formula PU is equals to A into FCD, right? This is the compression formula, so which we can see. Sorry. In the section 7 of IS 800/2007, we'll be having the design of compression member standards, right? So here you can see in 7.1.2 class, the design compressive strength will be equals to AE into FCD. So AE is here effective area of the column. So now by using this formula, we can calculate the area of the channel required, right? So first of all, for that we need to, we know the load 1080 kilonewtons, that is 10 cube newtons, right? So area is unknown, but the here stress is also unknown to us, right? So we need to assume the stress values. Assume design compressive stress, that is FCD as per our code book, right? So here there are some standards. If you are having angle sections, let me use some other color. Angle sections, then you can use 90 to 100 Newton per mm square stress. Or else if you are having simple I section or built up sections, you can use 100 to 120 Newton per mm square stress. You can assume in between this range. Or if you are having sections carrying heavy loads, then 125 to 175 Newton per mm square stress can be assumed. So here if you observe in this problem, the load is of 1080 kilonewtons, which is huge, right? So we can assume the load in the stress in between 125 to 175. Here in this problem, I am assuming the stress of assume FCD, design compressive stress of 150 Newton per. Calculate the sectional area required cross-sectional area. So using the above formula, 1080 into 10 cube equals to AE is an unknown and 150 Newton per mm square. So now the area which we got as a required area is 7,200 mm square after calculation. Okay. So by using this area, we need to assume some channel section. So the channel section, we need to check in the steel tables. So here are some channel sections. Okay. So among these channel sections, our area is 72 centimeters square. So here all the terms in centimeters. So I'm searching for the 72 centimeters cross-sectional area member. So here is one small correction. So this area is for two channel sections. So our entire design built up members. So for this entire section, we'll be having this area. So for one channel section, we need to take the area half of this. That is A equals to 72 by 2. That is 36 centimeters square. Okay. So now we'll see in the steel tables. So the area which is 32 we need, right? So here is MC 225 is having 33 centimeters square. So if you want to go little higher also no problem. So I'm going here with ISMC 250. Okay. So the section here I am assuming or considering is, let us try ISMC 250 at, this is the weight to the 298.2 Newton per meter. So these channels of 2 in number. We are considering. So now by writing the properties of ISMC 250 properties. So the properties of area is, so you can see the area is 3867 mm square, and RZ. So R is radius of gyration. So here you can see R values here. RZ is nothing but X, Rx. I think this is the one. 99 point. Radius of gyration is here only. So for IS 250, it is 99.4 centimeters, right? RZ is 99.4 mm and RY is 23.8. Here only RY. The thickness of the flange is 14.1 mm. So these are the properties which we got from steel tables, from table 5 of from table 5 of steel tables. And also previously we have taken some reference, right? For effective length, this is from table 11 of IS 800 2007. So we need to specify these codes everywhere. And also this formula is from class 7.1.2 of IS 800 2007. So now the area provided is 2 times the area of a channel. So that is 2 into 3867, which is equals to 7734 mm square. So now effective length was already calculated, so no problem. So then minimum radius of gyration should be calculated. So here is one condition. As we are spacing the channels back to back with some spacing S, so to calculate this, right? So here there are two axes, one is ZZ and one is YY. So here we are assuming minimum. Usually if you take a single channel section, minimum radius of gyration will be in Y direction. But here in this section, as we are spacing at some distance, so the radius of gyration will be in our hands. So we can keep the minimum radius of gyration as Z. Okay, radius of gyration as Z. That means in wide, we are spacing these two channels in such a way that the radius of gyration of Y will be maximum. Okay, so Ry will be greater than Ryy is greater than Rz. In such a way, we are keeping the channel sections. So here we are calculating the strength of this column, and to calculate this, we need to know the stress, right? So for that, we need to calculate KL by R value to know the FCD value. So in step 4, we are calculating minimum radius of gyration. So that will be equals to Rz, right? Okay, so now we need to calculate the slenderness ratio. As we already know the radius of gyration. So Rz is how much we have already taken it from the table, that is 99.4 mm. So now the slenderness ratio lambda will be equals to KL by R. So KL is already calculated, which is effective length 1 into L, where R is 99.4. Here N is 10 meters. So 10 into 10 cube mm, and that will be divided with 99.4, and the slenderness ratio will be 100.6036. But here in the class 7.6.1.5, here is a 7.6.1.5 class. Here, as they have mentioned, for the laced columns, the effective slenderness ratio of laced columns shall be taken as 1.05 times the KL by R naught. I mean general slenderness ratio, the actual maximum slenderness ratio, in order to account for shear deformation effects. To reduce the shear deformation effects, we are considering it as 1.05 times the lambda which we got now. Okay, so the lambda will be 1.05 into KL by R value. So that is 1.05 into 100.6036. So from class 7.6.1.5 of IS 800 2007. Okay, so now the calculated value here lambda is 105.63. So now for this KL by R or lambda value, we need to consider the design compressive stress. So in step 4, we are calculating or computing design compressive stress. So as this is a built up member, all built up members will fall in buckling class C. Okay, as per our table, here as per our table number 10, all the built up members will be having class C. Okay, so I'm taking this as class C, and now in a class C, for lambda values of 100 and 110, what are the FCD values? We have to note it down, and after that we need to find this for 105.63 by interpolation method. So from class or table 9C. Okay, so here from table 9C, design compressive stress for FY 250. We need to take this for FY 250 from table 9C of IS 800 2007. For 9C, 250 and 100, we are having the value of 170 and 94.6. Sorry, 107 it is. 107 and 94.6. So as I have given you one interpolation formula, so you can name these things as y1, y2, and this is y, x1, x2, and this is x. Okay, so we are calculating x value. Okay, so for that we need to take x1 plus x2 minus x1 by y2 minus y1 into y minus y1. So this is the basic interpolation formula. From this we can calculate the values. So x is here, in place of x we'll be getting FCD value for 105.63 lambda value. So here x1 is 107 plus 94.6 minus 107 divided by 110 minus 100 into 105.63 minus 100. So the value of FCD is now 100.02 Newton per mm square. So you can also cross check, like as this y or lambda value of 105 is in between 100 and 110. This x value should also be in between 107 to 94.6. Okay, so for this stress, we are calculating the strength. Step 5, calculating design compressive strength. So PQ equals to AE into FCD. So now the area which we have provided is 7734 into FCD is 100.02. So to calculate the thing in kilonewtons, we can multiply this with 10 power minus 3 as we are having this in newtons. So now the load or the strength we got here is 773.55 kilonewtons. Here, which is less than the actual external load of 1080 kilonewtons. So this is not safe. Okay, so now we need to increase the area. So because the initial stress FCD which we have assumed is an approximate value. So from there we are we are considering one section and we are trying with that section. This is our first trial. as this is not worked out, we need to increase the area of the channel and we need to change the channel section. Now go for the another channel. Okay, so 250 is not worked out, so we can go for ISMC 300 now. Okay. So for ISMC 300, let us try ISMC 300 at 351.2 Newton per meter to a number. Now the properties are area for this ISMC is 345.64 centimeters square. So 4564 mm square, and also RZ is 11.81. That means 118.1 mm, and RY is 26.1. In this way, we need to check because for columns to assume some section. If you have to design for a normal I section, then assume some I section based on the whatever assumed lambda or slenderness ratio values. You can get the stress values as we have discussed in the previous problem, or else you can directly assume some FCD value, stress design compressive stress value, and from that you can go with some random area and you can check like this. Okay, so now there are also some other values. So as our channel is placed back to back, we can take the gaze distance also for consideration. Right, so here for ISMC 300, the gaze distance here, these it is there. So this distance is 50 mm. Okay, and also the gaze distance is 50 mm. So I'll tell you why we have to take this gaze distance also. And width of the flange is 90 mm and IZ is 6362.6 into 10 power 4 mm power 4, and IY value is 310.8 into 10 power 4 mm power 4. So now these are the properties of our trial section 2. So now again the area provided is 2 times the area of this section, 4564, that is 9128 mm square, and L by R value. So R is LZ here, 10 into 10 cube divided by RZ is 118.1, that is 84.674. So this, then lambda value 1.05 times the KL by RZ, that is 1.05 into 84.674, that is 88.9. So to this value, FCD must be as buckling curve C, buckling curve C, Fy 250. And for lambda 88.9 means it will be in between 80 and 90. So FCD values will be from table 9C of IS 800 2007. We need to calculate this for 88.9. And for 90, it will be 136. And for 80, it is 136. And for 90, it is 121. And by calculating this FCD value, 136 plus 121 minus 136 divided by 90 minus 80 into 88.9 minus 80. Now the FCD value is 122.65 Newton per mm square. Now design compressive strength. PU is equals to FCD into AE. 122.65 multiplied by AE, area provided is 9128 into, so this is 9128 mm square. To convert, to calculate this force in kilonewtons, I'm taking 10 power minus 3, 11.1. So 1119.5 kilonewtons we got, which is greater than 1080 kilonewtons of external load. Okay, then this structure is, these sections are safe. So we can use IS 300 section. Now we have IS 3, ISMC 300 at 351.2 Newton per meter section is two channel sections are considered. Okay, so half of the portion of this design is completed. So now we need to place the in some spacing, and also after that we need to calculate the lacings. What is the lacing dimension and how much distance it should be kept and all. We need to calculate. That part will be discussed in next video. Thank you.